Okay, good afternoon, everyone. My name is Eduardo Todd. I will present the section about segmentation features and classification. I would like to introduce Vitor Barros. He will present an efficient method for porosity properties extraction of carbonate rocks. I gently ask you to make your questions during the presentation of the video, because after that we have 5 minutes for discussion. Okay, thank you. You can start.
Hello everyone, I'm Victor Cardoso. I'm a PhD student at the Informatics Center at UFPE, Brazil, and I will present the work entitled An Efficient Method for Porosity Properties Extraction of Carbonate Rocks. The analysis of petrophysical properties is of significant importance in the oil and gas industry. The information provided by the analysis allows more efficient extraction of these natural resources. One of the main strategies used for acquisition of these properties is the X-ray computed tomography technique. Through this method, it's possible to obtain precise virtual models of reservoir rocks and properties associated with conditions of storage and fluid flow inside the rock. Although the advances in this field of study have made it possible to obtain even more relevant results, conventional 3D image techniques tend to be very time-consuming and require a lot of computational resources. In order to improve the applicability of this type of analysis in the industry, it's necessary to use reliable and faster methods to perform the extraction of quantitative information about the porous medium. Therefore, the reduction of time in the micro-CT images analysis, capable of producing reliable results, represents a key challenge for the oil industry. Given that, the purpose of this work is to present a workflow that is capable of extracting petrophysical properties based on micro-CT image processing of carbonate rocks. The new approach is based on the automatic processing of 2D micro-CT images, and it was designed to provide results with low computational cost and demanding a minimum of manual parameterization. To validate the results computed by the analysis, we have compared the porosity data of 7 limestone plugs obtained with the new image processing method against the experimental data. The developed application used a new image segmentation technique to obtain porosity values more accurate than other image segmentation techniques evaluated. The calculation of pores orientation distributions with this new method showed good correlation with data provided by a conventional approach. In this work, it was possible to extract some petrophysical properties of rock samples in a shorter time than it can be achieved by a classical 3D image segmentation technique. Further sensibility tests allow to reduce the average processing time to only 26 seconds per sample, keeping the accuracy of the porosity calculation. Thank you for watching.
Okay. Any
Good
questions?
afternoon. I think this is the overview video.
Yeah, probably no.
Okay. Yeah, I think that's the complete video supposed to be extreme here. It's a doubt that I have.
Then you have more time to explain something else.
Because the complete video has about 15 minutes.
Yes. Hmm.
So
Well, if our support cannot do something now, maybe I can make some question to help you to explain
Okay,
your technique. Um,
okay,
I think we can arrange solve that problem. Um, what kind of image processing have you used in
okay,
the computer tomography to compute the porosity?
okay. Normally, the process, the extraction of characteristics of this kind of data, is normally based on the reconstruction of the 3D volume. At this time, the proposed workflow try to import the 2D, okay, the 2D images one by one and process them autonomously. And one important thing to consider in the analysis is how to pre-process the data and how to provide a segmentation that's capable of provide um, accurate results regarding the pore segmentation. In this case, the workflow has an algorithm to import the data and find a region of interest smaller than the original one to start to pass the information to the other steps of processing. After after the selection of the region of interest that is done autonomously, the next step is the filtering step, this filtering operation that was done by a Gaussian filter. After that, we proposed a segmentation technique based on global threshold segmentation that calculates the threshold value automatically based only on the histogram data.
Mm-hmm.
So at every imported image, the algorithm tried to find the threshold limit based on the histogram of each image according to the information that we had about this kind of data. In this case, is related to carbonate rocks.
Okay.
Okay,
The hosting format that is correct, so that is just the short video that is presented.
okay,
And
okay.
then you have to end your explanation. Okay, then you have handicraft method based on threshold to obtain the characteristics and then compare with histogram.
Actually, we use the histogram
Yeah.
to find the threshold limit and then
Yes. Okay.
apply the global segmentation, global threshold
Okay.
segmentation.
Okay. Mhm.
And then we cluster the image in two groups
Mhm.
in pores and rock matrix.
Mhm.
After that, start the steps of extracting information, extracting petrophysical information of the data,
Okay.
and
Mhm.
the information that are acquired with the workflow are the porosity that is simply the relation between the pores inside the whole area,
Mhm.
and the other information acquired are related to the morphological properties of the pore
Okay.
detected and regarding the area and the orientation. These properties are important in this field of study because they provided more information about how the oil will flow inside the rocks, and this can improve the recovery process when we are extracting oil and gas from the reservoirs. So, so after getting the information about the area and the orientation of the pores, we show the information in, as graphs as plots that we can find out how the porosity are distributed inside the rock. So there's possible to find anisotropy properties according to this porosity, because the porosity are a key factor. Oh, the pores are a key factor to determine how the
Okay, I have to cut you.
okay, okay, never
You
mind.
have 5 minutes plus five.
Okay,
Okay, it was possible to understand the general idea. The long video people can find in the platform, the
okay,
Google platform. And thank you for your presentation. Then I ask the host to prepare the second video. And I have the pleasure to invite Vargas to comment after that.
Hello, my name is Ibar. I present to you multi-level graph label propagation for image segmentation. That is part of my doctoral study. This is the outline of the presentation. First, I will talk about of introduction, then the contribution, then the related work, then the proposal, then the result, and finally the conclusion. In this work is about the problem of automatic image segmentation. In sometimes, for humans, it's very confusing to determine what is a best segmentation. It can be subjective from different people's perspectives. In this context, for computer, the complexity of the automatic image segmentation problem increases more. In graph-based segmentation methods, a graph is first constructed to represent the image, where the vertices are pixels and the edges are the weight between vertices. Then, segmentation is obtained using graph clustering algorithms. The large number of vertices and edges of the graph's representation is a motivation to propose new methods faster and more accurate. Graph clustering algorithms were used directly for automatic image segmentation. In this context, in some cases, information from the image domain has been omitted. Algorithms such as fast greedy, Lovine, and label propagation have stochastic results. This does not allow the reproduce of segmentation results. Fast greedy and Lovine are of multi-level nature, but label propagation is not. The multi-level strategy is useful for handling large graphs. The main contributions of our work are a multi-level strategy to create graphs that represent images in order to simplify the propagation of labels. Introduction of two deterministic traversal strategies to propagate labels suitable for image contexts. Propose a fast iterative multi-level method for color image segmentation based on label propagation. The fast grading method is of multi-level nature, and it was applied directly to image segmentation. The low-bind method is of multi-level nature too, and it was applied directly to image segmentation. The label propagation method is not of multi-level nature, and it was applied directly to image segmentation. In this context, we propose the multi-level graph label propagation method. The method uses information of the specific domain of image.
Okay. Okay, thank you for the presentation. No questions in the platform. I ask you, compared with other methods, do you have some comparison of performance? Okay. Oops. Okay, then we prepare the presentation of the following. The superpixel image classification is the presenter here. Oops. Ivara returned. Okay, welcome. You have 2 minutes. Then I would like to ask you about some comparison of your method with other traditional methods of image segmentation, graph-based.
Yes, I make a comparison with other methods, basically with complex network used for community identification.
Mm-hmm, mm-hmm. Okay. Another question? No? Okay. In less than 1 minute, we have the next paper, the superpixel image classification. Is some one of the next paper here?
Hello everyone, my name is Pedro and I'll be presenting superpixel image classification with graph attention networks, or GATS. The motivation of our paper is that since superpixels are groups of related pixels, they induce a natural graph representation by connecting adjacent superpixels and using some summary of the component pixels as the node's features. This can be seen in our example image on the left with its slick segmentation on the middle and its graph representation on the right. Therefore, the question here is whether we can use this much more compact graph representation for image classification tasks. And our paper attempts just that, using graph attention networks. The results of our paper are based on the 75 pixel benchmarks given by previous work, where an image is processed to generate approximately 75 superpixels. And as we can see, graph attention networks outplay all the other graph-based methods in the literature, which use a more rich k-nearest neighbor graph representation than the one we use, and which use handcrafted neighborhood aggregation schemes instead of using plain attention. However, we cannot match image-based benchmarks, not even simple schemes such as spot vector classifiers. The main reason behind this, which is further commented in the paper, is that the graph representation is too lossy, as we can see in the superpixel versions of the images, which already are quite hard to identify. The main takeaway for this study then is that GATs are a promising technique for graph-based image classification, being the best among other graph-based methods. However, there's still much room for improvement here. For example, using richer input graphs, data augmentation methods such as in GeoGCN, graph pooling layers, which are already available in the literature, and also investigating deeper architectures. The final goal of techniques such as this then could be to train on planar images, which have more data sets available, and then transfer this knowledge to non-Euclidean domains, such as spherical images. Thank you for watching. Look at the description for more information, and that's it. Thank you.
Okay, thank you for the presentation. Well, Pedro is here, good. I asked if somebody have some question. The platform, there is no questions. Okay. Then I have a question for Pedro. For some years ago, I have seen many papers about superpixel, and then I haven't seen no much more publications using superpixel. I suppose that you rescued the concept of superpixel, and which advantages do you see using superpixel in the graph attention networks?
As stated in the video, the main goal of this research, which is just starting, would be to apply the superpixel representation on planar images and then transfer the knowledge to a spherical domain. Current techniques with spherical images depend on convolutional networks, which are specific to the spherical domain, and thus you cannot transfer knowledge from the Euclidean domain to the spherical one.
Good. Okay, thank you.
Also, there was a recent paper, I think 2019, at the end of 2019, that did classification on superpixels as well.
Okay, thank you. One more question. Okay, if no, thank you for your presentation. We have 6 minutes for the next presentation.
Good morning, ladies and gentlemen. I am Daniel Ruiz, and today I will present our work. IDA, Improve Data Augmentation Applied to Salient Object Detection. Nowadays, deep neural networks are used to produce those salient maps, which requires a large amount of data. In supervised learning, this data must be labeled. In this particular case, it is required a pixel-wise annotation, which is time-consuming. This leads to certain biases on the datasets employed by the research field. Here is the position and size distribution of objects in a form of plots within the DUTS dataset, a common dataset used for training. There is a noticeable amount of images where the object is on the center of the image with large objects. Now take a look on the other publicly available datasets commonly used. While this bias is also present in some of the datasets, in datasets like Deuteron and Tur, the position is more widespread and contains smaller objects. This causes an issue, where the training data follow different distribution than the test. To overcome this issue, we propose a data augmentation technique that can approximate a source distribution of size and position to a target distribution. Our proposed method was designed to create new training samples by inserting salient objects from a source image in a new background image created by a process called image inpainting. Here are 6 examples of images generated by our method, where the top left image is the original image and the bottom left image is the source background image. The source background image has its object removed and then combined with the source object on the top left, creating the image on the right. The proposed method can be better understood by our flow chart here on this illustration, where you can see a set of images with their respective masks are selected as source objects, and another set of images is selected as the background with their respective mask. The object is extracted from its background, creating a foreground image only. The opposite happens with the background, where the object is removed using image inpainting. A feature vector A is then computed for the object I, and a feature vector B is computed for the background J. The K nearest neighbors method is then used to compute the inter-image distance between each vector. In this particular case, we use the cosine similarity distance. After computing the KNN, a foreground only and a background only produces an intermediate result. This result is then cropped and resized, and an image optimization is then performed to find the maximal intra-image distance. This ensures that the object is placed in a position and size that enforces a difference so that the object remains salient on its new background. Finally, affine transformation is performed together with image blending to generate the final sample. Choosing a good background is essential to maintain the salience. Here's an example of the qualitative impact of the background choosing. Here, there's a plot that shows the difference between the original dataset and the dataset augmented by our technique. The original dataset is on the first row and the augmented one is on the second one. Note how the positions are more widespread and the objects are concentrated on smaller objects. Here's some additional results obtained. Here are some of the qualitative results obtained. On each row, there's an image of a different testing data set. Thanks for your attention. Sem som. No sound.
Okay, Daniel, thank you for presenting. I see no questions in the platform. Since it's not fair that I ask you something, because I am also author, I would like to ask you to comment some of the big challenges you faced when working with this. The host has a question. You can start that and we check the question in the YouTube.
First off, main challenge I would say is the rapid progress of deep learning, because in a single year we have several different approaches which rapidly progress the I will answer the question next. With rapid progress the state of the art in the area. And salient object detection is usually used as a part of a greater project, usually when you need to speed up the entire process, where you don't want to process the entire team, but only the most attended regions. So we need a technique that is fast enough and generic enough to be coupled to this pipeline. And a problem with today with this approach is that you need label data. So label data is scarce because of the time-consuming process, and you need a lot of data augmentation to complement that. So that's where we found our most challenge, because you cannot apply random data augmentation, especially in salient object detection, because if you change too much the picture, the object is no longer salient. And a salient object can be anything. It's defined by the image itself. So I guess that's the main issue with the area. I don't know if it was clear.
We have two more questions. How do you define a good background? That was an interesting point. What are the characteristics of a good background?
The way we define a good background is based on, first we use all the images on the data set. So every image is used one time as a foreground and a background. But which is a good, we need to decide which one is a good background and which one is a bad one. So we use the difference, the cosine similarity between the two images. We use a hue, saturation, and value, and local binary patterns as well on our features. And the cosine similarity must be not the most distant one, neither the closest one. So we usually pick up the mean neighbor on the KNN plus the standard deviation. So it's not close enough and not distant enough, so it should retain some of the quality that we are hoping to achieve. Yes.
Okay, you in some sense preserve the degree of salience that you have in the original image.
Sorry, what? What was the question?
In some sense, you preserve the degree of salience that you have in the original image.
The salience is not guaranteed every time to be salient, but we try to maintain the salience by the intra-image optimization. So the object is always placed in a size and position that maximize difference between the foreground and the background.
Okay, and the last question, how accurate must the segmentation mask be?
Well, the segmentation mask for the label must be pretty accurate because it will interfere with the training sampling. But for the final result, the outputs from the entire process can be some more lenient because depends on the application you are using. If you just want a blurry region which you need to focus on, so a more blobby segmentation can be useful. But if you need something like removing a person from a background, you need a more accurate one.
Okay, thank you. One more question. No? Okay, then thank you, Daniel, for your presentation. Then we finished our session today. Thank you very much for all.